Hello, my name is Aaron Quigley from the University of New South Wales in Sydney in Australia. And thank you very much for inviting me to the Augmented Human Lab today for your symposium. And I'm delighted to be here, and I'm sorry I can't come across the Tasman to join you today. But I'd like to just talk a little bit about how we extend our capabilities and just think about all the times we're interacting with our bodies, the devices, the places we're touching, what we're moving around, the clothes we're wearing, everything that we actually have, the whole plethora of things that we may be, when we are wearing jewelry, glasses, our shoes, of course, you've got colleagues here who do that, the whole cornucopia of objects that we're interacting with on and around our bodies. What does that actually look like in a typical day? So let's just take a quick journey through one person's embarrassing body. Of course, we can leverage just our day-to-day interactions with our own devices, and we can think differently about how we actually do that. So we might start out with something, let's say, like Swim that we developed for just doing single-handed text entry and using it for doing shape writing in motion, hence the name Swim. And you can see here the little ball moving around the keyboard. But of course, this means we have to have a device, and it's not really our body that we're interacting with, or even just things that we might be wearing on our body. Well, we could extend it. We could look at something, let's say, like a ring that we might be wearing, and then imagining a keyboard in front of us and just moving our hand around this imaginary keyboard in different orientations could actually allow us to interact and allow us to give text input in a whole plethora of different situations. And all we'd be asking somebody to do is to just wear a slightly different ring than they might already be wearing. So we're not actually we're not adding to the types of devices so much. We're actually enhancing and augmenting the devices and extending the devices that they already have. But of course, rings and things that we have are extra things that we wear on us. What about our interactions and our the motions that we have, let's say, touching our noses or breathing and things like this? Could we detect those, and could we use those for new types of interactions? And why might we do that? Well, with Breathe In, we started exploring this long before the pandemic, but of course, since then has become much more relevant. Thinking about, when are people wearing face masks, in what kind of situations? Maybe they're wearing them in traffic, maybe they're actually wearing facial jewelry. And if they are, could we augment that? Could we detect the breathing, the speech, and the environmental noise? Could we develop a small MEMS and Teensy unit? And then could we do some simple processing on it? And if we could we actually then use it to detect short breathing inhalations and exhalations, a series of short inhalations and exhalations, and also some long breathing patterns. And this is what it might actually look like in the prototype that we actually developed. And then using that to power different types of applications. So let's say, control music, to start a running application, to start a navigation application, to send a message to somebody because you're in distress, whatever it actually might be. But of course, the challenges here are manifold. Detecting breathing just versus voice, just versus other types of environmental noise can actually be quite challenging. So there's plenty more work to be done here. Now, what about when we're actually just picking up other objects and we're moving them around on our body? So maybe putting on a sports putting on a sports collar, or putting a phone in your different pockets as you're moving around. Well, with RadarCat, maybe you could actually do that. So here we're actually training the system by basically placing objects in proximity to a sensor, extracting out a set of features, building a machine learning classifier, and then using that to power a whole host of different applications. And the one that I'd like to focus on today is around body part identification. Because here, as you're placing this type of instrumented device into different pockets, into your shirt, into your front and your back pocket, in and around your body, all of those different locations could actually be recognized. But of course, some of them might be misrecognized. And why might that actually be? Well, let's say your forearm, your belly, and your calf, they might actually be misrecognized because they've got similar constituent components. And as a result, a recognition system built on that might actually get confused. And of course, you also might want to try different frequencies when you're taking this type of approach. So what might this look like? Well, moving a device from a gloved to a non-gloved hand might trigger different layouts. Placing the device at different places on your body might actually trigger different types of applications, because you might want to trigger, let's say, a clock on the back of your hand versus a sports application when it's being placed close to your outerwear, versus being placed, let's say, closer to your stomach, a food application, or being placed on your outside of your shirt, just to recognize that, or let's say navigation if it's going to be somewhere else, or maybe a running application if you're placing it on your calf. There's a whole host of different things you can actually do. So suddenly the objects that you have can actually recognize where on the body they're actually being placed, and maybe use that to form new types of interactions that we wouldn't necessarily expect from our devices. Now we don't necessarily have to use radar to achieve this type of interaction. In one of our previous pieces of work, we tried this with optical recognition in the SpecCam system. So what SpecCam is actually doing is basically using the front-facing camera of your device as a multispectral light source. It's flashing a series of colors. Those colors are being reflected up into the camera on the front-facing device. Of course, they're very blurry, but all of that together actually gives you enough distinguishing characteristics to actually recognize a series of objects. Now here, of course, we're using it to, we're placing the device on different types of objects. But what you might actually want to be doing is you might actually want to be using it to detect material. So in this particular study, we tried different types of material, different types of clothing material, which are selected from common household environments. Now, with the spectrometer, which was our baseline here, we were only getting about 78% accuracy. But with this type of SpecCam approach, we were, with just looking at one color, we were getting 97% accuracy. But if we were flashing a series of up to 7 colors, we were getting 99.11% accuracy, which of course means that now, as the devices that you own, as you place them face down, let's say into a pocket, onto your jeans, onto a jacket, onto the clothing environments around you, in and around your body, all of that can be used to recognize those objects and can actually be used to trigger off different types of interaction. In the paper, we explored a sport vector machine and also a random forest classifier to determine different types of material and object classification. Now, of course, as I showed at the beginning, we're also interested in how you're interacting with your body using your hands. So you might be grasping your hands together, which of course could be recognized with one type of sensor, but also you might be interacting with your face or your ears or other parts of your upper body. So this brings us to Itchy Nose, which I'd just like to show you now, which is a discrete gesture interaction system using a simple pair of sensors. So the focus here is on interacting without distracting others, using the EOG sensors in the Jin's meme to actually achieve this. Now, what's nice in this work, of course, is that you can repurpose that sensor for other things. So yes, you can use it when it's on your face. What happens when you take the glasses off and they're on the table? Well, now you can use the same approach to detect different types of gestures that you might actually be exhibiting in proximity to the glasses. And I think this is what we all want to think about. Yes, we want to think about the time where we're wearing the glasses, when we're wearing the smartwatch, when we're wearing the smart ring. But when we take them off and we distribute them, let's say in our pockets or around us, they actually become an extended sensing environment that we actually can start to leverage. So for example, here you can see, like, you take off the glasses, you put them on a desk, but maybe you just put them on your shirt. If you're on your shirt, well, now suddenly your chest actually becomes a space for interaction. Now you might think, well, I don't want to do this with EOG, but Facebook is releasing glasses that have cameras built into them. Can we harness those types of sensors so that they're not just being used for recording photographs, but they're also being used as part of our sensing environment that we actually have on and around our body? Speaking of on and around the body, sometimes we actually have to think about how much of the body can we actually see. Now, in the episthenor work that we did, which was published a few years ago at the WIST conference, we were looking at this concept of having a smartwatch that would actually be able to have a camera, and all the camera could actually see is the back of your hand, not your fingers, nothing much else in the environment, although we have actually tried it with some IoT devices as well, but just the back of the hand. Now, if this device could just see the back of the hand, well, what could it see? What could you see just from this simple camera? Well, you might see some skin deformation, you might see some bone movement, you might even see some tendon movement on the back of the hand, or along with the web of veins. Now, if you took all of that information and you used it to train a system, maybe you could actually use it to recognize what the fingers and the hand is actually up to. So in our implementation, we repurposed a Leap Motion. We weren't using the Leap Motion tracking SDK in any way. We were just looking at a very small cropped, small field of view, mimicking what you might see from a smartwatch side camera view. This, of course, then allows us to build up different types of interactions, looking at, let's say, static poses, maybe looking at dynamic poses. So here you can see some static pose recognition. Now, again, if you look in the top center of the video, you'll see the shadowy image of what the camera can see. It's just seeing the back of the hand. So everything that I described previously is what's actually being trained for here, not the fingers, not the gripping motion, okay? Now, we could go on and actually think about how we would actually develop this. Well, in our approach, we took the camera data, we processed it, we split it in two so we could actually do dynamic poses. But for static poses, we just passed it through the simple inception network, this convolutional neural network over a series of layers. Of course, for this, it won't necessarily work for dynamic gestures. So that won't work because you've got temporal data. So with temporal data, what you actually want to think about is fusing it together. And that's where it comes to this two-stream inception network approach. So what you do is you take your raw images, pass it through one spatial stream, you take your motion image data, pass it through a second spatial stream, and you fuse those two together to give you the class score function for dynamic gestures. So let's have a look at what some of those might be. And here's some of the confusion matrix results. This will allow us to do these types of gestures. Again, you can see some static gestures here are being used to control applications. And now you can actually see we're actually using it to recognize numeric input, and those numeric inputs are being used to set, let's say, a timer, maybe dial a phone number, maybe play some music, different types of inputs to a system. Or let's say having a piano. But suddenly now your hands can be kind of part of the interaction space that you actually have with the world around you. So how much further could we start to take this? Well, we took it a little bit further in the WIS 2020 paper, where we were basically taking an RGB camera, the camera view that we had, but now we were looking at a dorsal net. And the reason to do that was to actually allow us to start to build up 3D hand pose estimation, because that hand pose estimation allows you to start doing a lot more than just doing the static pose data. So again, here you can see what the hand is actually doing. But now, of course, you can actually see recognition of piano input. So now just from the simple watch that you'd be wearing anyway, now you know what your hands are up to. Or at least you know what one of your hands is up to. You could maybe understand what keyboard entry is going on, and maybe grasping. And that's what I think is exciting about this work, is what objects are you actually touching? You know, stroking your hand through your hair, cups that you're picking up. But of course, there's some failure cases in here where it's a little bit too frenetic for the input. So here's some applications that we developed with it, you know, setting a timer, a virtual keyboard and a mouse, music players, all kinds of different applications that you would actually have. I'm coming towards the end of my 15 minutes and I don't want to run over because I know you've got a very busy schedule today at the conference. So again, I would just like you and everyone else just to think about, you know, our bodies aren't embarrassing. Like all the times we're interacting with them, we're touching them, we're moving devices around, we're wearing clothes, we're gesturing. All of those points of interaction are opportunities for sensing, opportunities for input, and I think opportunities for enhancing what it means to be human and enhancing our interactions with everyday devices. So thank you very much for having me. Good luck with the rest of your conference. I look forward to seeing some of the other talks when I can join you remotely in the future. So thank you very much and kia ora.